Hello, it's Brad here, and today what I'm going to be doing is quickly going through an example showing a conventional construction shear wall and how we go about doing the shear design, and at the end what I'll do is cover the seismic considerations as well. So if we take a look at this example, you'll see actually here in the mass file, I've just taken a screenshot just so we have a drawing to start with. So this is with a 15 centimeter block, 15 MPa. You can see it's put 10 M bars in here. They're just spaced you see 3 empty cells in the middle, so they're spaced at 800, so we have 5 corroded cells. So if I summarize it here, I'm just going to write a 15 centimeter, 15 MPa block. You can see it's 4 meters tall, 3 meters long in this case. And so since it is partially graded, we have 2 strengths that we deal with. So we have our hollow and our corroded areas. And the strengths, we can look them up in the CSA standards. So for hollow in this case, we have 10 MPa. So that's the unit strength of the face shelves. Then for corroded, we have 7.5. It's a lower strength, but that's per unit area. So since we have a larger area, we can resist higher loads there. So looking at this shear design, what I'm going to do is start by looking at the masonry component. So the way that we look at this in the software is we break it apart into different terms. So if we have our total shear resistance VR, we have our masonry term. So I'm going to do it in VR masonry. And then we have our VR steel. VR steel. This could be written as VS as well. It means the same thing. So if I look at that masonry component, it's actually masonry and axial load that we have together. So if I look at the equation, this is just taken right from the CSA standards, so that VR masonry, it's hard to read, is we have our phi m term, and then we have within brackets, we have 2 different terms. So our first one is the masonry, so it's lowercase vm, that's our unit masonry shear strength, multiplied by BW times dV, the shear depth, and we have another term, 0.25 PD, and all of this as well is multiplied by a gamma G factor, which I'll explain in just a little bit. So then going through these terms, we can look at, based on our wall here, we have things that we know and things that we don't. So for example, we know for sure our resistance factor is 0.6 for if we're looking at one of these. Our VM, I'll come back to this later because it has its own expression. The thickness of the wall, of this web in this case, is 140 millimeters, is our BW. And then our DV is, in this case, our DV is 0.8 times the length. And so if our length here is 3 meters, 80% of that is 2,400 millimeters. And then if we look here, we have our axial load. For this example, what I've done is I've just applied a lateral 45 kilonewton load. And I'm going to be analyzing it. And so the self-weight, we can calculate this ourselves. But just to speed this along, keep this video from being too long, our axial load, PD, is going to be equal to 25.4 kilonewtons. So that's this term that we have right here. And then gamma G is a term that takes into account, or it's supposed to take into account, the partial grouting of the wall. You'll notice that when we're looking at the masonry, we're using the full thickness, but we actually don't have solid material within this section. And so this gamma G factor, in this case, it's a little bit more complicated, where you calculate just the total area, taking into account these empty cells, and then divide that by your gross area. But since this wall is less than 50% grouted, in this case, it's less than half grouted. So we have a lower bound of gamma G that we can use. Gamma G is equal to 0.5. So that's our factor there. So we have pretty much everything except for this unit strength of masonry term that we have here, VM. And so it has its own expression, so I'm going to write it down here. Maybe I'll change the color just to keep it easier to follow. So VM, this is also just straight from the standards, so we have 0.16 times this term in the middle, 2 minus MF over VF dV. And all of this is going to be multiplied by the square root of F prime M effective. So in this case, because we're dealing with partially grouted, we have to take that into account. So where to start? You know what, I'm going to get right into that effective strength. So if we look at our cross section, I'm just going to do this down here. So if we look at our cross section, you can tell we have grouted areas and hollow. So you can see we have, I'm going to change my color again here. So we have 3 hollow cells here, 2 hollow cells here. So I'm just counting these, 1, 2, 3, 1, 2, just to give an example. We have 2 more here, and then 3 on this end. And so that's a total of 10 hollow cells. And then if we look at the grouted ones, we have 1 here, 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 here. And then depending on how fresh your counting skills are, we have 5 grouted cells. So then what we can do is, based on these areas, looking at this unit, I'll tell you right now, I mean, you can look this up, but our face shell thickness, TF, is 26 millimeters. And we have 2 of them within these. And so this has the higher strength. So if we want to figure out, we have some areas that have a higher strength, like these face shells here. It's really hard to draw straight. It's a smaller area, but that's 10 MPa, where we have these grouted regions here that have 7.5 MPa. So the question is, how do we figure out what an effective one is, averaging over the whole thing? And the answer is, what we'll do is we'll do an average based on looking at basically taking an average, weighting it by area. So what I'm going to do then for F per M effective, I'm going to start at the numerator. So I'm going to take the total area. So we have 10 cells that are hollow. Each cell is 2 face shells, so 2 times 26 millimeters. And then the length of these is 200 millimeters long. Oops. That's an extra 2, so 200. And then the strength of that is 10 MPa. So I'm going to write MPa there, so it's not confused with the 10 cells. The number just happens to be the same. And I'm going to do the same thing for the grouted. So this time we have 5 of these grouted cells. The thickness is 140 millimeters. And the length of each cell, once again, 200 millimeters is the nominal length. And that is all multiplied by 7.5 MPa. So we have that value there. I'm going to really focus and dig deep to try and draw a straight line. So far, so good. This is the content you all come here for. I'm going to divide it by the total area, so it's the same terms, just without that strength term. So 10 times 2 times 26, so 2 face shells, 10 of them. Each one is 200 millimeters long. And we're going to add that to 5 grouted cells, which are 140 by 200 each. And then, so if you put all of that into your calculator, you will get an answer when you get this. And when you put this in, 8.566 MPa. And so that is, if we treated this all almost as if it was one strength, not taking into account which strength is where, we get an average of this. And that's just because when you go back to that shear equation, this is the number that we need. So we have that. I'm going to scroll back up. So we have this F prime M effective of 8.566 MPa. So now we have to deal with this MF over VFDV term. This is actually something that specifically within the standards, there's only a certain range that can be included. So it actually, for this entire term here, I'm just going to see if this makes sense. If I draw an arrow. So it's actually, it has to be between 0.25 MF over VFDV and 1.0. So this is a value that actually varies along the height of our structure. If you recall, we have a lateral load being applied at the top, and so we have no moment at the top. At the very top of this right here, M equals 0. But then at the bottom, it goes all the way up to the moment, which is equal to V times our height. And so in this case, when we look at this, we know that when we are checking these numbers and looking at this, we're not going to get an answer that's the same for the entire height of the wall. And so you'll actually notice in the software, what it does is it brute forces it for each step. If you were doing this by hand, though, what you would be most worried about is figuring out what the critical section is. And so what I'm going to do is look at this at the base. So checking at the base, the reason I do that is because if you look at VM here, if I want to figure out where we're going to have the weakest masonry and axial load component, that is actually going to be checking at the base, and that is because just the way that the math shakes out 2 minus this term, whatever gives us this term the largest value, that is what is going to give us the lowest masonry unit shear strength. And so in that case, since we want this term to be as large as possible to find the governing value, then I'm going to take it at the base because my moment is not equal to 0. So in this case, and actually the way it works out is you'll find in many cases the upper value of 1.0 is what's used down here. And then when you work your way up the shear wall, what you will find is at the very top, you get that lower value. Because at the very top, you'll recall it's 0. So in this case, if we put in our numbers here, so if we have 180 kilonewton meters, and we want to divide that by our shear, which is 45 times that dV value, 2.4. If we actually put this in, we get 1.67. And so since that's greater than 1.0, then this entire term, we're going to take it as 1.0. So I'm going to write this here, 1.0. And so what we can do is we can go ahead now at this point, and we can calculate this. So VM 0.16, and that's times 2 minus 1. This thing is multiplying it by 1. And then we just need to plug in this number, 8.566. And so that is like we're going to square root that term to get that number. And so if we plug this in, what we get is 0.468 MPa. So that is a masonry shear strength. And then you recall that's the term that we're talking about up here. Okay, so now we have this value. So we know phi m, VM, we have these upper values. So I believe we have enough. We can go ahead and we can calculate this VR masonry. So I'm going to go back to the black colored pencil here. So if we go back, VR masonry, so this is equal to 0.6, and then we open up this bracket. We just calculated VM, so we have 0.468. Multiply that by 140 millimeters, and then our shear depth, this is 2,400. And then plus we have this dead load term, so 0.25. I'm doing everything in, so when you have MPa, you just need to be careful that you don't mix your units up. So I need to actually input this number in newtons, otherwise I'm not going to get very much of a component here and things kind of get out of sync. So in this case, that's 90%. Double check that in my notes. 0.9 times that 25.4. So in this case, 25,400 is how I'm going to enter this. And this is all multiplied by that gamma G term, 0.5. Okay, so I enter that into my calculator, making sure all my numbers are right. What you should get is a masonry and axial load resistance of, I'll get 48.889 kilonewtons. So that's the number that I get. And so that's what I'm getting from masonry alone. And you will notice that this is actually, even by itself, it is higher than just the 45. And actually, I took the screenshot from Mass after it had completed a successful design. So I already actually found that it had to go ahead and add horizontal reinforcement anyways. And so oftentimes with seismic, anything seismic, you have minimums that you have to deal with as well. And so it could be just that. I mean, I could have used bomb beams as well. This is just the default response. But in this case, I'm going to talk about seismic effects later. But this is an example where actually it might seem like you have enough resistance just from that VR masonry, but when it comes to actually checking more things, we'll find that we don't. So now what we can do is we can look at the joint reinforcement that we have in this design. So in this case, this is heavy duty. So in this case, I'm going to switch to using a red one here. So for our joint reinforcement, we have the heavy duty. So in this case, in the software, it shows up as 4.76 millimeter. That's the diameter. I think it looks like the word joint. Having a hard time putting that together. But in this case, actually, so this is the size we're using. So it's spaced at 200. So every single course, you'll see it there. And so the area of that, I'm just taking this from the textbook. The area AS, I'm going to write AS joint. I don't know how it refers to that in the software. But just for one course of this, still looking at 2 wires, one along each mortar joint, going along those bed joints there, 35.6 square millimeters. So 35.6 millimeters squared. So that is a helpful number to have. I'm just going to scroll down a little bit. And so if I want to go through and I want to calculate VS, so the steel component, or VR steel, so that is equal to 0.6 phi s. Now we have AS joint, the yield strength, and then we have it's multiplied by this term dV over, I'm going to write the spacing S joint. I don't know if that's easy to read. I apologize if it's not. So let's see. We know, 0.6 is the number. Phi S for deformed rebar for reinforcement, we're using 0.85. We know this value here is 35.6. I'm going to use 400 as my yield strength, MPa. dV, we figured out before, 2400. And then we have our spacing. If it's placed at every single course, that's 200. So if we go through and we plug these numbers in, I get 87.15 kilonewtons. Okay, so then if we go back to our main, I'm just going to scroll back to the top, you'll see here, VR is just the sum of these two components. So I'm going to switch this back to black here, switch my pen tip color. So now I can just add these together. So we have our masonry component, we have our steel component. So in this case, let's look at VR real quick. VR, we have these two. Okay, so we have 48, I'm just gonna 0.89 plus 87.15. If we add these two together, this gives me 136.04 kilonewtons. That seem right? Yeah, I think that's about right. Okay, so the only thing that we need to check is with this value here that we're not over the maximum. So there is a VR max value that we need to check. VR max, question mark? Thinking about it. So this is also something that's just taken straight from the standards. So I'll scroll down to give ourselves a little bit of room. So let's check that max. VR max, that is equal to, we have 0.4 phi m root F prime m effective. So that's the same value from before, F prime m effective. So we've already calculated that, times BW times dV. We have that gamma G showing up there. And this is multiplied by a factor 2. And that's minus the height of the wall divided by the length of the wall. So looking at that aspect ratio. So we know pretty much everything here. The only thing is that when it comes to this aspect ratio, we need not take it any higher than 1. So in this case, our height is equal to 4 meters. Length is equal to 3 meters. So in that case, it's a unit. If you look at H over L, it's greater than 1. So let's just go ahead and use H over L is equal to 1. So actually what happens is this entire term is just ending up multiplying by 1. So 2 minus 1. So if we go through, we plug everything in. 0.4 times phi m, so 0.6. We have our unit strength that we just found out available right here. So 8.566 times 140, the total thickness of our wall. The shear depth, 2400, multiplied by that gamma G factor, times 1, because this aspect ratio doesn't throw us off. We can put that in, and we get a number of 118.01 kilonewtons. So one quick thing to point out, you'll notice there's no area of steel here. It's basically just a maximum that we can count on from just the masonry. Had this wall being fully grouted, obviously this capacity would be double. And so a lot of times when you have walls that are partially grouted, especially with a lower strength masonry, you find you don't really get a lot of benefit from adding steel. And so in this case, since this is larger than that 136.04, we can conclude that VR is equal to that 118.01 kilonewtons. Okay, so then real quick, just one thing that I wanted to mention is that there are some seismic considerations that need to be taken into account. This is something that the software will do, but I'm going to quickly show you. So I'm going to write, what about seismic? Brad, things are going crazy. COVID sweeping the earth. What about seismic? That's what we're all wondering. And so actually what I'm going to quickly point out to you is that I've spent a lot of time writing and explaining these things, explaining the software's approach. I have a nice little disclaimer saying that it's up to you just to make sure that you understand what's going on here. So if you have any questions, please feel free. Do not hesitate to contact me, contact our office. We're happy to help out. But basically, I go through and explain the different clauses that come into play. So if I go all the way down, I'm going to look at the conventional construction. Here's the clause itself. But basically, we have two parts, part A and part B. I'm not going to really dive into them. I'm just going to quickly show you how it works for this example. So I'm just going to move it off to the side here. So in this case, what about seismic? I'm going to check these two limits. So basically, there are two different parts. I'll start with part A. And basically what that is that we want to ensure a flexural failure mechanism. And so actually what I mean, I'm going to go back to that article because there is a figure that will save me some time. So I go back up to looking at this part A. If we look at what's happening with our wall, basically we need to design for at least a shear force that corresponds to the development of the moment resistance at the critical section. So in this case, if we're looking at the base of our wall, I'm going to zoom in on this figure here, or I'm just going to direct your attention to it. I'm not sure if it's going to get much bigger for us. But in this case, you'll see this is a figure, a simplified figure of our wall. We have a lateral load, and then at the base, there is some moment, some factored moment that's being developed there at the base of our wall that we see. And then we also have a moment resistance along the height of our wall. You'll see it here as a straight line. I mean, technically, the difference in self-weight will change that a little bit, but that number is quite small. And so what this clause is saying is we need to design for shear so that we actually don't have a shear failure and to ensure that it fails in moment. So basically, we have to ask ourselves the question, how much would this load need to be increased so that the wall actually fails in flexure, or so that the factored load experienced at the base hits that? So if I look at this one here, basically what we do is we need to scale up this load so that our moment curve or our moment envelope along the height of our wall, it actually increases to the point where at the base of our wall, the factored moment is equal to the moment resistance. And so if I go through and do this, I'm just going to save you some time. But basically, if we, like what V or what lateral load would cause that, I'm just going to write VF seismic, and I'm going to put in brackets A because there's another requirement we're going to check. But basically, it's equal to that VF initial multiplied by the ratio, or basically how far our moment resistance is over our factored moment. So MR over MF. And so in this case, actually, just looking at its own, MR, if I go back, I mean, I don't show it in this calculation, but we have a moment resistance for this shear wall. So it's just a function of this cross section. Looking at these cells, some are grouted, some are hollow. With these bars, we have a moment resistance of 262.5. And that is in kilonewton meters. And the factored moment experienced at this is just equal to the shear multiplied by the height in this case. And since this is a seismic load combination, that load combo is 1. But in this case, we are looking at 180 kilonewton meters. So if we look at that factor, I wrote a V, MR over MF. In this case, we put these numbers in, so 262.5 over 180, we get 1.4583. So this is a 45.83% increase of that initial load. And actually, if we, I mean, we can just plug this number here. So we have, oops, the number is not 180, I'm thinking. So our initial shear that we have here, that lateral load, was 45 kilonewtons. If we multiply by that number, so 1.4583, writing is hard, this load actually gets scaled up to 65.625 kilonewtons, okay? So I mentioned there's two parts. This is just part A that we're looking at. And the way that the CSA standards say is that you need to check these two limits and you need only increase it to the lesser of these two. So let's look at part B. So if we, part B, once again, if you want the details, please just go check out the post. But this is looking at our, we have these factors, these SFRS force modification factors, RD and R naught. So since this is conventional construction, we know RD is 1.5, or I said R naught, it should be RO, because that's for overstrength. RO is 1.5. So when we calculated our loads, this is even before anything that I showed in this example, we got to divide our seismic loads by these factors because we're absorbing energy. We do have extra strength that we're not counting on. And so in these cases, it really benefits our design. But basically, what these clauses are looking at is, well, what if RD, RO was only equal to 1.3 as a hypothetical? Well, that is a great question. And so in this case, for conventional construction, like I said, 1.5 and 1.5, if we multiply those two numbers together, so RD, RO, in this case, 1.5 times 1.5, we get 2.25. So our loads, we got to divide them by 2.25. So the question is, what if we only divided them by 1.3? So in this case, VF seismic, I'm going to put B here in brackets, is equal to that initial VF initial, which was the 45 kilonewtons. Basically, we're going to undo the fact that we got to divide it by 2.25 when we initially calculated our loads, and we're going to scale it up as if it was 1.3. So what we're going to do is we're going to multiply this by this factor of RD, RO, and we're just going to divide it by 1.3. The value that was put in here is our hypothetical. Well, what if we only got this much? So we take that initial 45 kilonewtons, we're going to multiply it by 2.25 divided by 1.3. And so then what we get for our limit for part B is a number that's larger. Let me check here. 77.88 kilonewtons. Okay, so we've got our limit for part B. We have 77.88. If we go back to part A, we get 65.625. So based on this clause that we're following, we need only take the lesser of the two. And so in this case, this is our governing one. And need not be applied. So I've got that written there. So we checked both of them. We only need to use the lesser. So in this case, it's still a pretty big increase. And like I said, 45.83% increase. But we are still well above our VRs. Actually, if I want to summarize this, so first of all, our factored shear when we're checking this, VF, after taking into account seismic, is going to be, I'm just going to write 65.6 kilonewtons. And then compared to VR, this was after checking against the maximum and everything, we have 118.0 kilonewtons. And so our resistance is well over our factored. And so we can declare this wall is adequate. And so once again, if you have any questions, this is all things that are done internally within the software as well. And so please feel free to reach out if there are any issues that you come across. As always, Canada Masonry Design Center, we are available as the technical support provider for the software. And so please feel free to reach out if there's any questions. Just about version 4 in general, activation, installation, whatever, just give us a call. We'll get you up and running. Thank you.